Now, because I suck at making plugin tutorials, let's just do a nerdy rambling deep dive on the SG-323 in Reactor. It's built with blocks framework, and if we go to the process block, there we are at the top level with all the inputs, outputs, some other stuff, and this one, oh god, it's just called macro. I should have renamed this one. 323 process. So this is where all the magic happens. Okay, this one looks like a giant spaceship, but let's go through it from the input to the output. So first we have our input stage. This is where just the left and right input come in. There's some gain applied. We have a high pass filter at 4 Hz, which is just for DC filtering. And then we have the trim port from the input to change the volume of the input signal, the mute button, then there's some gain applied again, and both of the signals will be summed together. So the reverb is effectively a mono input stereo output. Now the input signal will go as well to the direct left and right output. So if you just listen to the dry sound in the plugin, it will be, of course, the original stereo signal. But that's really boring, so let's get down further into the reverb. First, there's some pre-emphasis filter, which is a high shelf at around 3000 Hertz. And then we're already summing the feedback together with the dry path. But we get back to the feedback later. Then we have the high-pass filter and the low-pass filter, which are both controllable from the front. The high-pass filter will be adjustable between 14 and 480 Hz, and the low-pass filter will be adjustable between 48 kHz and 3 kHz. This is all pretty basic stuff and just macros from the Reactor factory library, so nothing creative here. Then we add some digital noise, which is generated here. This is just a workaround for now. The original hardware unit that I have, when you listen to the longer reverb programs without any input signal, you can hear the quantization noise of the downsampling and the converters, and this really makes up part of the sound a bit, and I try to approximate this with some noise added to the reverb feedback path, but this is just a basic workaround for now. And then we have the anti-aliasing filters. So these filters are to prevent any frequencies above 16 kHz to enter the actual delay path. And what I did, I custom designed several elliptic low-pass filters in MATLAB, depending on what sampling rate you're using. So the original also uses elliptic low-pass filters. And what's so fancy about elliptic filters, they have a very sharp cutoff, but they have some frequency warping in the pass band and a stop band. And I tried to get really close with all those filters to the original filters in the hardware. And this clock distribution macro is also from the blocks development template, and it's really handy because that way I can just check, okay, depending on what sampling rate you're using, only the filters that are actually needed for this particular sampling rate will get a clock signal and will use CPU, and the other 4 filters will not use any CPU. So, but why do I have like 5 filters in here? The thing with these elliptic filters, at least when you implement them with the direct form 2 that I did, is that when you design them, they are always designed for a specific frequency sample rate in mind. So when I have a sampling rate of 48 kilohertz, I will have different parameters to get a cutoff point at 16 kilohertz. When I have a sampling rate of 96 kilohertz, those will be different. And to make sure that on any sampling rate I have the cutoff and the frequency warping at around the same, I need several different filters. And as you can see, I have some for 32 kilohertz, which is the original sampling rate of the hardware. So if you want the most authentic sound, but then the analog signal would suck. But anyway, you can just set the reactor ensemble to 32 kilohertz. I have a filter setting for 40.1, 48, and 96, which are the most common sampling rates used. And if you use any sampling rate outside of that, like, I don't know, 88.2 kilohertz, do people use that? I don't know. But if they do, or 192 because you're a frequency snob or whatever, then there's just a basic low pass Butterworth, because I won't make the effort to create separate filters and all the stuff just for some frequency rates that only weird people use. No offense. Then here we have some gain applied, and now we have a sample rate reduction. This one is taken from Michael Hetrick, also known as Unfiltered Audio, from the Bitcrusher 1.0 blog from the user library, which is also available for free. And because I have not been able to come up with a solution of my own, for now I've just copied them from his blog. Same goes for the Bitcrusher blog. So because the original unit only has a sampling rate of 32 kilohertz and a signed 15-bit memory, I try to approximate this behavior by using the sampling rate reduction and the Bitcrusher that will limit the samples to 16-bit. And this here is just a helpful function to choose the amount of sample rate reduction depending on what sampling rate you're using. So when you're running the ensemble at 32 kilohertz, there will be no sample rate reduction applied, but if you run it at 96 kilohertz, it will automatically pass the correct parameter to here. Now we come to the memory. Oh yeah, okay, so we do, right now I do have two memory blocks. One is the legacy block, which will give the correct outputs if you run at the original sampling rate of 30 kilohertz. But because people don't want to run, especially if you use it in blocks together with other effects, you don't want to run everything at 32 kilohertz. And so to make it possible to use it as higher sampling rates, of course you could do that anyway, but then the decay times will be much shorter. And to make sure that on 48 kilohertz, 44.1, 96 kilohertz, whatever, you get mostly the correct decay times as well. There's two different blocks, one for the original 32 kilohertz setting and one with interpolation for all the other sampling rates that people might use. So the delay times, so if you look in here, it's lots of the same stuff, because internally the Stargate 323 has 23 delay lines, like 23 single separate delay tabs. 15 of those, like the first 15 in here, up until this point, are used for the feedback signal, and the next 4 are used for the left output signal, and the last 4 ones will be used for the right output signal. And for each of those delays, we have separate settings for the delay time, as well as the gain and modulation settings. So this is basically just the same thing 23 times. And where there was going to be a... Whoops. So how do we get those delay times? Here we have this address counter, which is just is it 14-bit? Oh god, how many bits are those? Yes, okay. We have a 14-bit write address, and all the delay times will be depending on the current write address. So each cycle, the incoming sample will be written to the memory, and all the delay tabs will just read it from there at different times. So the write address is a 14-bit value, and then we have the feedback tabs. And I'm not trying to get into too much detail because this is really, really messy, and but it's all based on how the original hardware works. So I've looked at all the different integrated circuits, what each of those does with the signal path and the delay calculation, and replicated this behavior in here. So for each of those 23 delay tabs, there will be a separate value for the delay time and the gain modulation of this delay. And this is exactly what happens here. We have let's get to the original one, which is a bit easier. We have the write address, which writes it to a 14-bit memory, and then we have all the 15 and 8 delay tabs, which will just get the read address and put it out to a bundle. Speaking of bundles, they're awesome because previously I had lots of spaghetti code in here. Let's get the old one in here so that you can see how it looked before I cleaned everything up. So yeah, this was how my internal structure looked previously, which works, it's fine, but it's really tedious to debug, and if you want to change things and if you want to whatever. And Reactor has this nice feature called bundles, which you might know from the, let's see here, which you might know from the sample rate inputs on many of the filter and delay macros. And what it essentially does, it's just a separate macro where you have this bundle input or output, and as many inputs that you like, you can say for each one if you want it to be a float or integer, and you just give each of them a separate name. Like here, so I have FB01 to whatever, like the 15 pickups for all the 15 feedback signals, which then get packed into this bundle. Same for the output tabs. And then on the other end, let's follow the feedback tabs. So all those feedback tabs will get summed together, and they always will also get a gain value applied. So as you can see here, maybe if I do a split view, it's more obvious. Okay, so yeah, maybe this one. So we have the feedback tabs, which how you name the output for the bundle doesn't matter, but it's really important that you name the pickups the same. And then in here, where you have connected the feedback tabs, I have another macro, which is just an unpack. And there we have the bundle input and all the same pickups with the same names. And that's everything you need to do. You just need to make sure that the pickup in the pack and the pickup in the unpack macro have the same name. So like if I change this to 12, then it suddenly will show me, okay, there's something wrong, this doesn't exist. And yeah, so, and I did the same for the, let's close that because it's confusing already. And I did the same with the gain values. So if you look at the feedback tabs, we have this one bundle for delay and one for gain values. And what's also really neat is when you're using the bundles, you don't have to unpack everything. So I could have put the delay and the gain pickups into the same large bundle and feed them to the same place. And at one, I just unpacked all the delay ones, and at one, I'll unpack all the gain ones. But yeah, so we have the 15 feedback signals coming in, and we have the 15 gain values coming in. And then each of those feedback signals gets multiplied by gain value. They all get summed together. This is something that I find really tedious in Reactor. Maybe there's a better way. But just to do summing of several different signals, because you need to create those large tree structures of adding. And then they're all just divided by 15, because otherwise the signal would be way too large. And the same I'm doing for the output tabs, except that there's just 8 tabs with 8 gain values in a two pairs of each 4, and so they're only divided by 4. Now, those structures here are essentially the same like with the anti-aliasing filters, because like I said, there's a DRAM array for the 32 kilohertz setting and one with the interpolation for all the other sampling rates. And I have another clock distribution macro depending on the sampling rate of Reactor. And this will send a clock signal to either only the interpolated delay or the legacy delay. And with those macros, or those... what's that? Those read-write macros will just clock the incoming signal depending on what sampling rate you're using. So that if you're using a higher sampling rate than 32 kilohertz, all this will not generate any outputs and will not use any CPU resources. Same goes for this one. Then, yeah, there we just add those together. But either way, one of those bundles or one of those wires will be 0 anyway. And now we have another shelving EQ, which is the opposite of the pre-emphasis filter. So there we have this high shelf with a gain of 6, and there we have the same high shelf but with a gain of -6. So, and another anti-alias filter, which is the same as on the input for each of the 2 output signals. And then those go to another mixing macro, and it's just some multiplication, adding, addition, whatever. And then it goes to the output. Now let's follow the feedback signal. The feedback signal will be multiplied by 0.63 and will be inverted. It took me 4 months to get there. Like I literally had everything working, but the feedback wasn't sounding right. And I adjusted the value, I tried everything, and the decay times were correct, but it sounded wrong. There was some weird resonance going on. And then after playing around with this simple value here for 4 months, I even started looking at the schematics and going over everything again to see if I missed everything. And then one day I just thought, what if I inverted? And everything fell into place, and I felt really dumb for like taking 4 months to get to the idea of putting a minus here. And I still don't know why this needs to be inverted, but it sounds right, so I'm fine with that. Yeah, then we have 48 kilohertz low pass filter, which is just a one pole. Same for a simple high pass filter. And this is a dip filter at 9 kilohertz, so it's really small. Even in the original circuit, it doesn't do much, but I guess it's needed to tame some of the resonance or some of the feedback overshoot. And this is a state variable filter, which usually only has low pass, band pass, and high pass outputs, but there's a pickup macro to convert the output to a peaking or shelving, peak filter, bell filter. And then we sum the feedback together with the input signal, and the feedback will have a gain of 2.16 applied. And this value is also just chosen on the gain value that is in the original analog circuitry at this point. Now, what else do we have? Yeah, it's pretty much it, I think. Oh yeah, then we have all the modulation is based on a modulation counter, and there's a random number generator, which this is also a bit weird. So as you can see, the input signal in here goes to several places. We already had the some mono signal that goes to the reverb path. We have the direct signal for the left and right outputs, and then we have this R&D signal, which is used as the input for the random number generator. And here I just have some parameters to play around with, and I think for now the random number generator is still the thing that is not as close to the original hardware than I would like, but it works, and I'm still working on it. But it already sounds okay as a whole. Oops. So what it does, it takes the input signal, this is just a scaling value that I applied, and applies some really narrow filtering, like a 370 hertz low pass and a 106 hertz high pass. So the frequency range that you get out of this is just like 250 hertz. And then it will be then we have a rectifier. So because this signal is bipolar, like it goes to plus and minus values, and this one will rectify it so that we only have values between 0 and positive. Yeah, so this one makes sure that we only have values between 0 and some positive number. And there's a DC filter again. And then we compare it to one of 4 values. And if it's higher than any of the values, it will generate a random number on the output. And this random number on the output will be used as the input for a random counter. So in that case, it's not really random, it's pseudo-random, because once you figure out how the signal comparison relates to the input signal, it's should be pretty much linear. And yeah, here again, you can see those C0 and C1 signals, which are the clock signals depending on what sampling rate we're running, because this is also different for the modulation counter. And here's also some scaling for the modulation counter. And whenever the modulation counter reaches its highest value, it will reset and send a clock signal. That's the randomization counter. There's so many counters in this thing. Anyway, once the random counter reaches its top value, it will just reset and send a clock signal to the actual modulation counter. And this will be used as input to randomize or modulate the delay and gain values of all the tabs. And yeah, so all these weird, complicated structure and dependencies, I obviously didn't come up with that by myself. It's all based on how the original hardware works. And it just took me like 18 months to figure it out, because I have it's in the original one, it's all discrete logic, like all those old logic chips. There's no CPU in there, nothing. So it's very, very early digital circuitry, which makes it really easy to understand if you know what to look for, but I didn't know what to look for. And so, yeah, at least I know now how latches and gates and bit shifters work. Yeah, so that's my rambling deep dive into the Stargate 323 circuit. And yeah, I hope you have fun with it and create nice sounds, and we'll put it to good use.